Hello. So search is not anymore only based on the traditional approach that we know, which is term-based search, but more on the machine learning trend where new models have opened a new era for search. So this talk is giving an overview of what is the classic search and the limits that we have today. What is the ML model and how you can use it? I'm sure you have listened to a lot of talks about AI, but I will cover that maybe again. How to use vector search and hybrid search in Elasticsearch, and how ChatGPT from OpenAI or the similar large language models easily play with Elastic. So the main idea of this talk is to show you how you can build on top of your existing Elasticsearch clusters and with all the features that you already know. At some point, I will show you some of the features which are under the commercial license, but there will be this label on the slide. So don't be confused when there is no when you don't see the label, there is no. It's not commercial. You have the access to this with the basic license, but when you have this label, then it's commercial. So you will know. Anyone here in the room attended my talk in 2017? It was 6 years ago? No? Nobody? Okay. I was looking younger, anyway. It was a Java live coding session about moving your legacy search to using a database to Elasticsearch. So I'm really happy to be here again in this city. So Elasticsearch, you know it's for search. Who knows Elasticsearch here? Okay, many of you. Some of you? Okay. So Elasticsearch is I would say, the search engine you can think about nowadays. It's based on Lucene, where you have all the foundations, the needed foundations for the engine, and really often contributed by Elastic. And this includes all the work that we've done with the vectors. So do you know this sentence from this iconic movie? Okay. So these are not the drawings you are looking for. If you are indexing such a text in Elasticsearch, you will go through what we call an analysis process. And this analysis process is basically composed of multiple steps, like a character filter, a tokenizer, and some token filters. Those are explained here. And when you want to index this text or search for this text, actually the text you are seeing here in yellow is going to be indexed or parsed that way, like you have droid, you, and look. Okay. So what is the problem with that? If I'm searching for machine and not droid, it's not going to work. Of course, we can fix that with synonyms, but okay, it's not out of the box here. And also here, these are not the droids. And here we have droid you look. So maybe it's the negative side of it. What about image and audio search? Here we are only able to search for text, right? And so it's the default implementation is very simple and it scales very well. It works okay for text, but not for the overall. And instead of that, we would need more semantic search. And semantic search is totally different than literal search, like term-based token search, right? So what is semantic search? So today, or maybe yesterday, we are asking questions like token-based X-Wing Starfighter Squadron. But in the future, what we want to ask, and maybe the future is now, is what kind of ships or crews do I need to destroy almost a finished Death Star, or is there any secret weakness or something like that, right? So Elasticsearch, you know, it's for search, but maybe you don't know it's yet for vector search. We started this journey like 3 years ago to implement the vector search in Elasticsearch. So I need to first cover what is a vector to explain all the details, and so you will understand the internals. Doing a smile for the photo. So embeddings. Let's talk about embeddings. Embeddings are basically numbers which represents your data. So here I have Darth Vader in the dark, maybe, and here I have the Princess Leia. So this is a picture, and this is a cartoon version of Darth Vader, right? So I have an axis here, a vector, and on the right I want to see if it's more a cartoon, on the left if it's more realistic or not. And then I can place my images on this vector, like Leia is -1 and Darth Vader is +1. Of course, I can add multiple dimensions. Like here, I want to have another characteristic of my images. Is it a machine or is it a human, right? So here we have a robot which is realistic, but it's a machine. Here we have still Leia, who is a human, but realistic. And this one is a human, but a cartoon, and Darth Vader is half human and half machine, right? And then you want to add multiple data, and we are going to group together the similar data. So if we are adding Luke here, we can see that Luke is not exactly human because we cut his hand, so that's the reason. So we have here some coordinates to represent all our data sets. And then when you want to do a vector search, what you are going to do is to evaluate, to search for this person, for example, put that here on the embedding space and try to find what is the closest data that you have. So here, probably, we are expecting that Princess Leia will be the closest person to Han Solo. What you will have to do that is to choose an embedding model. So my advice for that is to start with off-the-shelf models. You have plenty of models on Hugging Face, Microsoft E5, for example, OpenAI's Clip. And if it does not work for your dataset, then maybe you can change and tune that a bit, apply some hybrid scoring. We will see that in the session, but also bring your own model. And with the demo that I will perform, you will see that I'm going to bring another model. Actually, I'm going to use a model which is existing. Be careful between training and the actual use case. It's like if you are training yourself to run 100 meters and then going to a marathon, it's not going to work. That's the same thing for the data. Use the right training and really compare with your actual use case, actually. So how it works when you want to run a search. So you start with documents, and what you want to do is to index documents. So whatever the documents are, you want to transform the content. It could be text, it could be image, it could be sound, into dense vectors. So the embeddings that I mentioned previously. And then when you want to search, you do exactly the same thing with the query, and you go through the same embedding process, the same generation of embeddings, and then you try to find what is the nearest neighbor and to find the result. So let's cover the first part, how we can index vectors into Elasticsearch. So if you know Elasticsearch, and if you don't know, this is what I'm going to cover. When you want to index a document, let's say this is the text representation here of an e-commerce website. So this is the content. I have this JSON document which represents this data. And what I'm normally doing, I'm posting the document to Elasticsearch. And Elasticsearch is indexing all the fields. If you want to do vector search, what you need to do is to generate the embeddings that I mentioned before. So with whatever system you want, it could be Python, it could be Java, it could be whatever you want, and then transform and generate these embeddings here as a field. So for example, the description that I have here, this text, I can generate also embeddings that represent the meaning, the semantic of this text as vectors, right? And because I can do that for images as well, maybe I can generate an embeddings to represent this image here and describe the image. If you have the commercial license, you can generate the text embeddings, not the image embeddings yet, but the text embeddings using directly Elasticsearch without the need of another service running. So we have inference pipelines inside Elasticsearch, and if you load your machine learning that you loaded, for example, from Hugging Face, then we can use that to generate on the fly the embeddings for text. We have a script which allows you to import easily the model that you want. So here you choose the model that you want here, and then you just and it will run inside Elasticsearch. So Elasticsearch supports a different range of NLP models. So you have the field mask model. I like this one. It's like you have a text and you have empty space inside, and you ask the model to find the words actually that should go to this text. So entity recognition, sentiment analysis, and what have you. You have the full link with the documentation here if you want to look at this. So how do you search vectors now? We have index vectors. How does it work? So what you do, you take your text, the query, you go through the same embeddings, the same embedding generation that we saw previously, and then you generate a vector here, and you run what we call in Elasticsearch nowadays a KNN search, right? And you provide the embeddings as the vector, as the input. So this is the representation of this text here. And then it will search. I will explain that. Same with the commercial license. You can generate the embeddings directly with the machine learning models that you loaded into Elasticsearch. So you just provide the text and what is the ID you want to use, and then Elasticsearch is going to generate the vectors for you automatically. So to run a vector search, those are the needed components. You need to have the search part. So in Elasticsearch, the query is the KNN search. For the index, you need to provide the right mapping into Elasticsearch, which is the schema into Elasticsearch. And for that, you need to type your field as a dense vector. And then you need to generate the embeddings. So for text embedding, you can use the machine learning if you have the license of the commercial license, but otherwise you can run that locally from a third-party tool or what have you. So how does it work? Let's do some math a bit. So let's say that I have here two documents indexed, so those two vectors, D1 and D2, and then I want to search for Han Solo. Right, this is the query. So what I need to do is to compute actually the distance between the two vectors to find what is the closest vector. And we are fortunate in math, we have the cosine, and the cosine is basically going to compute what is the distance between the two vectors. So if we do some math, it will be something like this. So if the vectors are super close to each other, then the cosinus is going to be close to 1, which means that 1 plus 1 divided by 2 equal 1, so we will have a score of 1. On the opposite, if the vectors are totally opposites, then the cosinus will be -1, so we will have a score close to 0. And then we will move this score around those two values, right? So this is how we can compute things. So this is the default implementation into Elasticsearch, but you can ask also for whatever reason you want to compute the distance using the dot product. And the dot product is going to basically put this vector on the document and compute, including the length of the vector as well. And another one is L2 norm, which is the Euclidean distance, and where here we are just, really comparing the value of the points. We are doing a sum. There are some optimization here, like we are doing a square on the square root. That's it. Yeah, sorry for my English. I'm French. So this is in French-English, by the way. So here, this is some kind of optimization, but basically this is going to give you the same output. So we have seen the algorithm behind the scene. So now how we can compute that. So The first thing we did was brute force with the first implementation. So it was taking a lot of time to compute all the documents, all the distance between the query and the documents. So it was not that ideal. But there is one popular approach that emerged then, and we implemented that as well. So this is the hierarchical navigable small words system. So basically we start from one layer and then we are trying to find the closest match using layers. I'm not going to cover that in details, but this is basically what we have. So it's a bit less accurate, I would say, but we have an excellent query latency when you have a lot of indices and a lot of data. We are actually doing both things. So depending on the number of documents we are going through, then at some point, if we realize that HNSW is not efficient enough, we are going to do the brute force instead. So we choose that automatically for you. We are contributing a lot on Lucene, so and we are making fast progress there. So we have supported until 2048 dimensions, and recently, actually, we increased that number to 4,000, more than 4,000 dimensions. So that's a lot. That's a lot does not mean that you need to use and you must use all the dimensions, because this is coming with a price, actually. So vector search needs a lot of memory. We need to hold the tree that you saw previously in memory, basically. The indexing process is slower because we are sending a lot of big vectors into Elasticsearch. So it takes some time to index that. And there is also something which is happening behind the scenes on Elasticsearch, which name is merging. So we are merging to rebuild the index every time, and this process is slower. Even though we are doing a lot of improvements. So some of the best practice, if you want to implement that with Elasticsearch, avoid searches during indexing, exclude the vectors from source. I will show you an example of that in the demo. And then reduce the number of vectors, and instead of using floats, you can maybe convert to bytes. That could be the same meaning for your use case, and that will be much better. So if you want to reduce the required memory, what you can do is to reduce the size. So instead of using float, as I said, you can use bytes. It will consume less space. And also, maybe you don't need all those dimensions. So maybe you can also reduce the number of dimensions that you are going to send to Elasticsearch. That could be a good thing to do. There is a lot of things happening in the field about vectors. So don't trust anybody, right? Just do your own test and test in your condition with real data, and you will see what is the best tool for your use case. I'm pretty much confident with Elasticsearch because we are a search engine and we have been built for that, but anyway. You have also this nice repository, which is doing benchmarks about all those vector stores, so you can also have a look at this one. So currently, Lucene is in the middle of the pack of the benchmark, which is not bad because you know that we are using Java, so we don't have all the nice hardware acceleration stuff that native language has so far, so which is good, but we are making still progress again. So we have seen that Elasticsearch can do vector search, but now we can combine actually the term base score with the vector similarity score. So this is called hybrid search or hybrid scoring. So what we want to do with that is to take the input from the user, do a term search as we are used to do, and add also the vector similarity score and combine all that with boosting. How does it work? So this is typically a query that you are going to run. So the search API. So this is the term-based score here, so running a match with this text on the description field. And we use the same summer clothes representation, the embedding representation of this text, and we do that against the desk embedding part to adjust the boost of each part depending on your use case, which maybe it's a bit tricky. We'll cover that in a moment. You can do the same thing for the image, for example. So you can associate text with the image search and title search with the representation with your embeddings. We are providing out-of-the-box Elser as part of the commercial license. So this is not dense vector or token-based search, BM25, but it's sparse vector. So it's what we call text expansion. How does it work behind the scene? If you are looking for, so if you run, the simulate API on the ingest pipeline and say that you want to use the inference processor that we have and use the model ID which is built in, the Elser one that I just introduced, and use this for this text, you will see that we are not going to generate the tokens that we saw previously, but we are going to generate something else. So we are going to generate synonyms out of the box. So it will be super fast than when you query because it's still a token-based search. The cool thing with that is not only synonyms, but it's synonym with a weight. So depending on the weight, it will be taken into account. So it's giving a lot of very good results. I said that you can combine the score. The problem with that is that you don't have always the same way of ranking things or computing the scores. So instead, what you can do is to use RRF, which is a way to actually combine all the scores together. So let me show you an example of that. So let's say I want to combine the score from here, the BM25 approach, which is not the legacy, but the old-fashioned way of doing search. Then you can also add Elser here, the text expansion that I mentioned, and then do the vector search, the KNN, and then with all those three sources for the results, then you can combine that with this rank fusion approach. How does it work? So let's say that you have from one algorithm those documents that are coming back with those scores, and with the second ranking algorithm you have those scores. You can see that if you are just mixing those scores together, all those documents won't never appear, right? It's not the same kind of ranking. So instead, you are going to ignore the score, but just use the ranking. So what is the position of the data, the rank position on the data in the result set for this ranking algorithm? So 1, 2, 3, 4, 5. And then you add a number, so 60 by default. Don't ask me why, but it's 60. And this is giving you a value. And you do the same thing for the other algorithm. You compute that, and you have another set of values. And then you do the math, which is explained here on the top, and you do the sum. And then it's going to reorder depending on the rank, not about the score anymore. Right? So this is super powerful, actually. Okay. Let's do a pause here, and we are going to do a demo, I hope. So I like DJing. This is what you said. Wow. Oh, you are. Yeah. So, shameless plug. If you want to scan this one, you will have access to my podcast. I'm kind of beginner in this field, even though I started a long time ago, but I like doing that. Oh. Siri is starting. Why Siri is starting? I love that. Okay, anyway. So my demo will be based on music. So what we are going to do, we are going to search for music. So the purpose of this demo is to actually index some audio files. I'm going to generate embeddings using an algorithm. I don't know exactly what the algorithm is doing. And it's going to generate embeddings. And for each audio file that I have, it's going to be stored into Elasticsearch as a vector. And then the purpose of the application, it's not real an application, but you will you can imagine what it is. Let's say that I'm humming a song, something like that. Then it's going to do the same embedding process, generate the embeddings for my query, and I will try to find what is the closest match to what I just sung, and then give me back the result. So let's try that. Yeah. Okay, I hope it's still running. Let's see. Otherwise, yeah, probably it works. So I have installed everything here in this notebook. I'm not just, so here, this is the model that I'm using. I'm not sure what this thing is doing, but anyway, this is the model. I'm connected to Elastic Cloud here. So let me check that I'm still connected. Yeah, okay, cool. So I have created an index, an Elasticsearch index. And what I want to mention here is that I have this audio embedding part. This is where I'm going to store the vectors. Those are dense vectors here. I'm using this cosine similarity that we saw. And what I'm doing, I'm excluding from the source the audio embeddings. Okay? Yes, this is what I mentioned previously. And I have overfills here, which are not super important. So I have created all that. And I have some code. So the code is listing audio files, not really super fancy. But this part is more interesting. What I'm doing here, I'm generating embeddings from the wave file. So I'm loading with a library the content from the audio file. And then I'm running with the model that I loaded, the inference, and I'm generating the vectors from that. Okay. So this is not coming from Elasticsearch. This is coming from another third-party library, I would say. And then I normalize the data, and I'm returning that. And to index the data into Elasticsearch, what I'm just doing, I'm providing the content that I want to index. So this is exactly what you saw previously in the slides. So I'm passing here the vectors, and this is what I'm indexing into Elasticsearch. And when I want to search, actually what I'm doing, I'm running here the KNN search that I mentioned, and with the embeddings that will be generated by the software, and I'm running this search. So let's have a look at the audio files that we have. So I have all those audio files. So I'm going to generate the embeddings and index all the documents into Elasticsearch. What you can see here on the right is the start of the vectors, right? All the vectors that I'm generating. So I have some of them. It can take some time. Okay. And then the goal of this is to find a similar song. So let's do that when it's done. Almost. Okay, it's done. So I want to find a similar song of this one.
Na 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 na.
Okay.
Na 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 na.
So what I need to do, I need to generate the embeddings. This is what I mentioned, using exactly the same process that I use at index time. Again, that's important. I can show you the list of the embeddings. Okay, so this is looking like this. There is a lot of data here. I don't know what it represents, but this is the representation of this file. And then I can run the query. Okay, so it's done. So this is the JSON version of the result, but not super meaningful here. Here I'm going to just look at the 5 first hits that I have here. So I have, obviously, the first one is the same file. Of course, they are totally not close. They are the same vector, so those are identical. That's normal. But if I look at the second one, so this second one has this score. And if I look at this one, So it's me. I was humming the song. I'm super proud because the machine actually recognized my tune as the best approach for this. So that's cool. If we look at the second one. Okay. So it's not Shazam, you see here, because Shazam will not exactly match the two things. Shazam is super powerful, but it's not going to do the same thing. Here, let's have a look at this one. Okay. So it's the same tune, but with another way to interpret this tune. And then I have this one. Why not? Absolutely not related, right? But kind of humming song, so maybe that's the reason it's up here. But normally what you want to do is to take the first one of the list, because, or the second one in my case, because this is the closest document that you have. If you want to run again the notebook at home, then you can do that. There is also another demo with another song, but whatever. So, yeah, what time is it? Yeah, I still have some time. So let's talk a bit about ChatGPT, because ChatGPT changed the world. And let's see how Elastic and LLMs are actually working very good together. So let me change that. Yeah, so maybe you have heard about that generative AI is going to remove the need of search engines. I don't trust that, because maybe I'm biased, I can confess that, but I'm pretty sure that search engine can play a very good role together with generative AI. So let's cover a bit what generative AI is doing. So basically you are asking a question, and you are sending this question to generative AI. The generative AI is trained on public internet data, and obviously it does not know everything about your dataset, I would say, and it's sometimes because maybe it's not running in real time. I don't know. So, and you are getting one answer. What I dislike about, by the way, this answer is that the answer given by the system makes you feel that this is the right answer. I'm used to say that the LLM things, or ChatGPT tools, you need to take them as a friend. A friend can affirm you something that this is the answer, but maybe it's not, okay? Maybe it's wrong. So this is the same thing with those tools, right? So what I asked ChatGPT, okay, what is the current version of Elasticsearch? So it's saying the truth, actually, because this is the last update. So I ran that some days ago, and it was 7.10. We are at 8.11, but okay, it's outdated, I would say. And you know, how much money do I have on my Revolut personal account? Sorry, but I can assist with that, which I was expecting, because I don't like that ChatGPT has the details of my bank account. So indeed, it does not have access to that. So what you can do, let's say that you want to combine all the things. You have your business data, and you don't want to send your business data to a third-party tool, but you just want to be able to search within your business data, whatever it is. So you can ask your question, get back from your business data with Elasticsearch the results. It can be using terms-based search, vector search, or what have you. Use that as the input of a context window, and just give the result to the generative AI or LLM stuff to give the right answer on your dataset with a natural language, I would say. Okay, so I'm going to run a demo for that. So here I'm going to use Elastic, plus I can choose one of them, whatever you want to use. Okay. So let's do that. Mm-hmm. So here, I have a demo. I'm connected to the wiki pages, basically. So I have indexed the wiki pages of Elasticsearch. And I can ask this question. what is NASA? What do you think is going to happen here? It's normally the national agency, right? But here I'm connected to the wiki. So what is giving me? It's giving me back that, okay, NASA refers to the North America, South America region within the sales organization, which is exactly what we are expecting, right? So, and I have the link, by the way, to the documents that Elasticsearch found, and those are the documents, not the documents themselves, but the extract, the snippet of the document that have been provided to the LLM thing to then generate the response, right? So this is what we did, which is cool because if you don't have the answer, then it's not going to generate anything. So, for example, who is Thomas Pesquet? I hope he does not know. So it is a French astronaut, if you don't know. Okay, he does not know. Of course, if you send that to your LLM and you don't have this filtering before that, then it's going to answer a question which is out of the context of your business. Right? So here you are combining the two things. Bonus point, because you are in Elasticsearch, you can also filter the data. Let's click here, I think. Yeah. So for example, I'm going to ask how does compensation work? It's saying, okay, I don't have enough information. Indeed, here in this demo, I'm an engineer. I don't have access to this data set because it's another part of the data set. So with a simple filter, I can exclude or include documents. So here, let's say that I am a manager now, and I can ask the same question. And obviously, it's going to generate a really tailored document, send that to the OpenAI stuff here, and then give me back and produce the response. By the way, I can choose maybe AWS. Why not? Does it work? Cool. Yeah, so I have also the answer. So this is a way to combine both of the worlds, and I think it's a very good implementation to have that on top of your data. So the conclusion, yeah. If you want to have a vector database, you need to be able to store, search for vector embeddings. If you add machine learning, so this is what we have with Elasticsearch with the commercial license, then you can create out-of-the-box vector embeddings, and then you have a search engine plus the semantic search engine with all the features that you already know into Elasticsearch, like doing aggregation on top of your result set and things like that, doing navigation and whatever, autocomplete and what have you. So you can combine the both worlds. So Elasticsearch, you know, it was for search, but it's also for vector search. Just later in the other room, I'm going to have this talk about enriching postal addresses with the Elastic Stack. So we will cover bits, Logstash, Kibana, Elasticsearch, and so on. Oh, I have to say a word. What is that? Let me check. The word is Dekoju? Yeah? Okay. So thank you for attending, and have a nice day. Thank you.